All right, the recording just started. Okay, let me do an introduction very quickly. So again, my name is Wenming Yi. I'm a product manager for open source machine learning tools at Amazon AI. And this particular user group is started by a group of folks from Amazon, as well as folks at the Rapids team at NVIDIA. So our goal is to help for folks, whether you're new to GNNs or whether you have been here, been doing this for a while, to essentially create a community for folks to get together and talk about GNNs or graph analytics. So today we have a pretty full agenda. If you're new to this particular group, so I definitely will encourage you to join our Slack channel. So the Slack channel is this bit.ly link. And I will post that into the chat window so that everyone can get a copy of it. I have to figure out where's the chat window here. Grace, could you do that for me instead? So I'll have you do that. And then the event happens every essentially the last week of each month. Happens every month at 4 p.m. Pacific time zone. So the last time it was January 28th. We had 3 speakers, and this time it's February 25th. And next month it's going to be the 25th as well, I believe. 25th of March, and we will be sending out reminders for folks to join. So today we have a full schedule. So DGL 0.6 release will have an announcement. So Mingjie Wang from the DGL team will be making that announcement for the first 5 minutes. And then we'll have Professor John Owens. He will be talking about Gunrock, which is a very popular graph analytics optimization tool. And of course, I'll let him talk about all the other research that he'll be doing. At 4:30, our friends over at NVIDIA, Joe Eaton, will be talking to you about CuGraph, which is a GPU-accelerated graph analytics tool. And then at 4:55 to 5:15, Dr. Chuan will be giving a talk on exploitation on learning mechanisms on GNN. From Beijing University of Posts and Telecommunications. And finally, we'll have about 20 minutes to have an open discussion. And we also talk about job postings, among other things that is relevant to this community. So with that, I'll let Mingjie get started.
All right, I've shared my screen, so can everyone see it?
Yes, we can.
Okay, cool. So, yes, thanks, Wenming. So my name is Mingjie. I'm from AWS Shanghai AI Lab. So I will briefly talk about the upcoming DGL 0.6 release. And for people who don't know what DGL is, it stands for Deep Graph Library, which is a specialized system for graph machine learning. So check out our GitHub and homepage. So in this release, we'll bring actually improvement on several directions. First of all, new documentation, then new model examples, and also improvements on the system usability and efficiency. So first, documentation. So we know that documentation is very important for open source project, but writing a good set of documentation is always a very challenging thing. And in DGL, we adopt this idea called the documentation Hanoi towers. As you can see here, we organize different kinds of documentations in multiple levels, and they serve different purposes. For example, for absolute beginners, you'll start from a brief introduction and then gradually learns about the tutorials on different topics. A central user guide will serve as like a manual book for people to look up different using scenarios, probably some corner using cases. And finally, we have API references and developer guide to cover more details. And in the last release 0.5, our focus is on the user guide, and we also rework the whole API references. That are done, and in this release 0.6, we shift our focus from the lower level to the upper level. We introduce, we release a set of tutorials called Bliss Introduction to DGL, which a user can finish in 2 hours. And also tutorials on advanced topics like mini-batch training for graph. And besides, we translate our user guide into Chinese thanks to the community effort. Of course, people may ask, where are the developer guides? We didn't forget that. We will schedule it in the 0.7 release. So let me elaborate a little more on the new documentation in 0.6. First of all, this brand new Bliss Introduction to DGL in 120 minutes is a set of new tutorial that will teach you of these very basic tasks, such as using DGL to accomplish node classification, link prediction, and graph classification, these kind of fundamental tasks on graph machine learning. It also covers the most important and also the most common components that a user will use when using DGL, such as the graph object, the GN module, and the dataset. We also release a set of tutorials on the topic of mini-batch training or stochastic training of GNNs. This topic is more advanced because the stochastic training of GNN is quite different from normal like SGD of like image classification or NLP. And for this set of tutorials, we step by step teach you how to train GNNs with neighbor sampling for node classification or link prediction. We also illustrate the core idea of the neighbor sampling algorithm using animation like what you see here. Okay, next, the new model examples. First of all, we actually have a new model index, which we organize all the models by their topics and by their publishing time. So if you click that link, you can see that it is basically something like this. Okay, so let me see here. So you can see here, this is the official DGL example index, and it actually ordered all examples by their tags, notable tags like their target tasks, and also whether they use sampling algorithm or something like whether they have working examples on OGB dataset. Okay, next, we add more examples, of course, to DGL, but we not only consider the quantity, but also the diversity. In 0.6, we have 11 new models, and many of the new models are on new topics. For example, we have new models on data augmentation, normalization, and hypergraph, which are missing in the previous release. And we also add models not only to GN research, but also to domain research, like computer vision, point cloud, and also to different type of graphs. Finally, we have some improvements to the usability and system efficiency. On the usability side, DGL now supports half precision training or mixed precision training. And we also have a utility called Graph Data Loader for graph classification task. And there are 2 experimental features called sparse embedding and distributed heterogeneous graph. On the efficiency side, DGL now fully integrates with PyTorch's native memory management, which avoids a lot of unnecessary CUDA malloc and CUDA free. And we have faster module implementation like RGCN, and also faster kernels on both the CPU and the GPU. Okay. And from 0.5 to 0.6, there are a total of 284 PRs of all kinds of fixes and patches. And we calculate that roughly 1/4 of them actually come from external contributors. One more thing, the DGL team is actually co-hosting a workshop on graph neural networks and systems in the upcoming venue called MLSys. So if you are interested in submitting papers, please visit this site, gnsys.github.io, and we welcome any submissions. Thank you. And I will pass my mic to Ming.
Thank you, Mingjie. I'll let Professor John Owens take over the screen sharing. There you go.
How's that look? Sound okay?
Yes,
Graphics
perfect.
okay?
Thank you. Yeah,
Okay.
Everything looks great.
Great. Well, good afternoon, those of you in America, especially for my colleagues in Texas. I hope you're getting through this okay. My name is John Owens. I teach at UC Davis. I am delighted to come and talk about the work that we're doing on Gunrock, which is our system for doing graph analytics. Let's see. I'm not talking about GNNs today. What we build is a system with which you can do graph analytics. And one thing you could possibly do with graph analytics is write GNNs. We're very happy to point to a piece of work that was done using Gunrock, so built on top of Gunrock to do GNNs. And so it has open source, and that's terrific. But what we're trying to build is the engine. And as people are interested in using something like Gunrock, our job is to make it as easy as possible for you to write GNNs, write systems, test them, and so on. So my expertise is generally on GPUs, and the concern we generally have with using GPUs is that you kind of have to be a ninja. If you're going to make, if you're going to turn to the GPU, which is a challenge to program, it better give you some advantages, and it means that you really need to, run it at its peak. That's the value proposition. You're willing to go through perhaps a little bit more pain to get higher performance, and so it requires that you be able to reach that peak, to be the ninja that programs this. And our job is to try to close that ninja gap as much as you can. That I get to work with a large group of phenomenal graduate students who are ninjas, one and all. And what we're trying to build is a ninja-like weapon that you can use to do any graph analytic that you would like to. So the system we built is called Gunrock. Let me tell you just a little bit about where the name comes from. Gunrock was a horse that was brought to UC Davis in the 1920s, and he was a descendant of some other famous horses, and he became the namesake for the UC Davis mascot. It's also the name of the pub on campus, but I will assure you that the naming has nothing to do with that at all. We started writing Gunrock in 2012. DARPA had a program called XData. It was their big data initiative. And one of their goals was that the outcomes of that were all to go open source. So we started by actually trying to write individual graph analytics and make them fast. And we rapidly came to the conclusion that what we needed to write was instead a general engine with which we could build any graph analytic rather than customizing to a certain graph analytic. And it took us it was nice because it was a very long-term piece of research. We didn't feel pressured to have results right away or papers right away. And the first paper that we had wasn't for 4 years later. But we extended that to going to multi-GPU same node. And in 2018, we became the performance reference for DARPA Hive, which is DARPA's initiative for building hardware and software for doing graph analytics that was 1,000 times better performance than the state of the art. So, I tell my grad students, if you can make Gunrock run 999 times slower than that system, then we've won. But we're very proud to be selected there. We're also really proud to get to work with NVIDIA in their Rapids initiative, and Joe will talk about that next. But Rapids is now shipping with some Gunrock analytics under the hood, and we've really benefited from working with NVIDIA's engineers, both technically and because they bring really interesting problems for us to solve. So let me sum up what the programming model is of Gunrock in a single slide. So we've got a graph. It has lots of nodes and edges. And we are going to choose a subset of either nodes or edges, and we're going to call that a frontier. And the idea behind Gunrock is that all computation we do are operations on frontiers. So it's really a data-centric kind of programming model. The center of the whole programming model is this idea of having a frontier, and then you manipulate that frontier. So things you might do, you might filter a frontier and get a smaller frontier out. You might compute on every element of the frontier. The one that's probably most performance interesting is an advance, where you have a frontier of vertices, and then you want to return the frontier of all the vertices that are connected to your input frontier. One thing that's unique about Gunrock is that it supports frontiers of nodes and it supports frontiers of edges. And so having that mixed capability and being able to have an input of one type and an output of another type from a particular operation ends up giving you a lot of flexibility. Now, when we build apps, what they are is just sequences of these operators. They're bulk synchronous, much like the traditional GPU programming model, although we're experimenting with more asynchronous kind of programming models here as well in implementations. And why is Gunrock fast? It's because we put a lot of effort into the load balancing issues that are associated with doing operations that are irregularly parallel. And I'll talk about that in a little bit more detail, but when you're trying to build fast graph analytics on a machine like the GPU, that turns out to be the biggest performance challenge, in my opinion. So what we're trying to do with Gunrock is 4 main goals. One is we want it to be really fast. We want this to be the best of breed. We want this to be performance competitive, if not better than anything else that's out there, even hardwired implementations. 2, we want it to be general. We want all sorts of graph. If you have a graph analytic in mind, we want you to be able to express it with Gunrock. 3rd, we need it to be programmable. Not only must you be able to express interesting graph analytics in Gunrock, we also want it to be straightforward to write them. And I would say of our efforts, that's pretty much one of the places we're putting the very highest effort. What can we do to make that programming model as simple as possible? And then we want it to be scalable. And so we've done some academic work that shows that we can certainly expand it to many GPUs on a single node. That's what Hive is having us look at now. And we're interested in moving beyond that, both in terms of scale up and scale out. So you can use Gunrock apps in, I'd say, 3 different ways. One is you build this on your Linux box. There's command line access to run whatever analytics we have. Matrix market files are the way that we input graphs. 2 is if you have existing code, we provide C linkage. Python linkage is kind of there. We haven't had so much interest, but direct interest, but we know that that's something that's interesting. But from my point of view as a low-level engineer, what we're interested in is really building your own. And so what the programming model shows is to say, okay, what is the data that we have to be carrying around in our graph? And then how do we sequence these operators to actually do the graph computation that we care about? When do we stop? And then we have nice support with testing and validating your code. And we're not professional software developers, but we have tried to go to an enormous amount of effort to try to make this an adult, high quality software project with real testing and regressions and plots of our results and so on. So the website, I hope will give you some interesting information about that, but we're really trying to do a good job with our software methodology. So one thing I think you'll find with Gunrock that's superior to at least other GPU graph frameworks is that we support a large number of primitives. And I think one criticism I have of the academic community is generally we look at textbook primitives. And so every paper is going to have results for BFS, single source shortest path, connected components, PageRank, and betweenness centrality. And they don't really go beyond that. And so because we've been working with DARPA and because we've had good suggestions from NVIDIA, we have broadened our idea of what we see as interesting graph applications. And we are trying to go beyond sort of these narrow textbook ones that academics generally look at. So this has really driven our programming system and the primitives that we've built to look at a broader set. You're not supposed to get much out of this slide except to see that some dots are blue and some dots are orange. And so we've done some comparisons against the state of the art in many different areas, both CPU and GPU, both hardwired and programmable. Blue dots are the ones where we are better in comparison on a particular application, and yet orange is worse. It's a little bit dated. It's a 2017 paper, but I think we've generally kept Gunrock, pretty near the ceiling in terms of how fast we can run graph analytics on a GPU. In a much longer talk, I would talk about the challenges that we faced in terms of building this. But specifically, I want to talk about 2 of them that we found to be particularly interesting. So one is irregular workloads and 2 is dynamic problems. So I think the biggest challenge in terms of building fast graph analytics is to deal with having a workload that is irregular. And so if we think about how to parallelize a typical frontier operation, you've got this frontier of vertices. And each vertex has a certain number of neighbors, and the easiest way to parallelize that is to parallelize over that frontier of vertices. So assign, say, one thread to every vertex. The problem is if you do that, you get a large amount of load imbalance because some vertices have only a few neighbors and some have potentially a very large amount of neighbors. And so some of your hardware, a lot of your hardware is going to be idle as you finish the vertices with the highest workload. And so we have to go to a fair amount of effort underneath the hood of the abstraction to be able to balance these so we can keep our hardware busy. We spent a lot of effort on this. We've published a fair amount in the academic literature as well. So a couple ways that I'd like to point out that we look at this. One is a static method based on prefix sums, where you basically convert parallelism over the vertices, which is really irregular, to parallelism over edges, which is much more regular. So it takes some pre-processing to do that, but it gives you better performance overall. Another strategy is a more dynamic one where you bucket work. So you say, well, this vertex doesn't have very much work. We're going to bucket with other ones with a similar amount of work, and then we're going to be able to run them efficiently. And so we have a number of heuristics that helps us choose these. The cool work that we're doing right now is we're trying to separate out the capabilities we have for load balance into a standalone library, because we know load balancing, fine-grained load balancing like we do in Gunrock, can apply to lots of different operations as well. For instance, sparse matrix, sparse vector, sparse tensor kind of operations. And so that's a PhD dissertation that's well on its way in my group. The second challenge that we've recently taken on that I think you'll find interesting is dealing with dynamic graphs. And so the input to virtually all GPU graph analytics work that I see is typically expressed in a format like compressed sparse row. So it's very space efficient, gives you good memory patterns, people use it everywhere, lots of input files and so on, but it's an immutable format. You know, if you wanted to go into the middle of that file and stick in one additional edge, you have to pick up half the file and move it. It's just not a format that you can change very easily. And there's been a decent amount of work on GPUs that has tried to target this. You know, do we have a list of edges? How do you actually allocate those? Fixed size or variable size? Linked lists of fixed size arrays? But basically all the previous work when it was developing data structures to represent dynamic graphs like the ones that we would like to support, it would use lists. And I'm going to tell you why we think that's a bad idea. So for instance, you want to make a query, does this edge exist? So what you're going to do is find the edges that are attached to a particular vertex. You're going to look in its data structure. And the question is, do you sort that list or do you keep that list unsorted? So if it's sorted, you can look through that list and do a nice binary search and pretty quickly return whether or not that edge is present. But on the other hand, whenever you do updates, you have to maintain that sorted order, and it's a fair amount of work. It's much easier to maintain an unsorted list, but on the other hand, when you have to search through an unsorted list, you have to look at all the items. And neither one of these is desirable, and it's kind of something you're not really going to get around. So what we've done is work where instead of using lists as the fundamental primitive, we're using hash tables, and it's dynamic hash table work that we've also done in our group. And so when you do queries into hash tables, if you build them right, they're very fast. They're O of 1 kind of access, but also insertions and deletions are also very fast. And so this is the foundation of the branch we have of Gunrock that deals with the dynamic graphs. One of the concerns we have in general is we kind of built this without a good set of workloads. There's this chicken and egg problem where we would like to do dynamic graphs, but there aren't really good workloads for them. And so nobody builds dynamic graphs as a result. We believe that there's a lot of interest in this. There should be a lot of interest in this, but we sort of did the work without really knowing exactly how it's going to be used. So if you have dynamic graph workloads, we would love to hear about them. We also did an implementation of graph analytics using the graph BLAS implementation. So this is, I believe, the fastest GPU graph BLAS implementation. It's called Graph Blast. We have an open source implementation of this. We also have an archive paper that's been submitted to a journal. So I'm really proud of this work. We have a fantastic student that led it that's since graduated. And if you're interested in the Graph BLAS, this is a really cool project to look at. Just wanted to mention a couple concerns that I have about graph analytics on GPUs going forward. One is this issue with this focus on textbook applications. And I think work that only focuses on these textbook applications ends up focusing very heavily on advance, as opposed to some other operators that we also have found are important. And it doesn't build programming systems that really expand to things beyond textbook kind of applications. The other thing our community does is it focuses a lot on computing apps rather than science apps. And that's why I'm so happy that Rapids has taken an interest in NetworkX, because NetworkX has a lot of workloads that are much broader than the kind of compute centered applications that generally our community focuses on. Programmability is another concern that I generally have. And I would say I say this top sentence all the time to my graduate students, but in talking to customers of ours, there's sort of three ways we think people are going to want to use graph analytics. And the third one was a little surprising to me, so I'll call that out last. One is we just want to use standalone Gunrock primitives. Great, we certainly support that. Two is I'm a ninja programmer. I want to write my own stuff. I want to sequence my own operators. No problem. You know, it's what our grad students do all the time. But the one in the middle was kind of the interesting one, which is I want to take an existing application and it's going to have all these interesting compute steps in it. And I'm going to want to just change some of those compute steps. It doesn't take a lot of ninja status to do that. It's like, well, I'm going to change this ranking. And we want to make it easy for people to do that as well. We see that as a really viable way of using Gunrock that we expect will be more popular in the future. I wanted to call out some of what we learned in our DARPA effort. One is that DARPA gave us a whole range of really interesting workloads that we implemented using Gunrock. One of the nice things was that Gunrock was able to target all of them. We're happy and proud of that. In general, this is more than anything what motivated our focus on Gunrock programmability. Another issue was that there was just a lot of big workloads where we just wrote the graph part, but it's very clear that Gunrock plus X, whatever X is, linear algebra or optimization or neural networks, was a really interesting focus, at least from DARPA's point of view. I think the thing that surprised me the most is we were kind of expecting that the workloads would look like full Gunrock application, something else, full Gunrock application, something else. But it turned out that instead we were interleaving Gunrock components with other components in a much more fine-grained basis, right? And so that motivates having graph analytics frameworks that really support user programmable pieces. And that's what our applications look like. And then data structures, dynamic data structures, good high performance range of GPU data structures really became a need as we're looking at Gunrock, and that's another research focus of our group. In general, scalability continues to be a concern. GPU stuff doesn't generally go to the greatest scale. We've done some preliminary work on that just with BFS, but it is certainly a direction that we'd like to go in the long term. And I'd like to thank all these amazing people that I've got to work with along the way on this project. Thank you.
Thank you, Dr. Owens. I would like to open the floor for questions for the next 5 minutes. If anyone would like to ask them, you can also put them in the chat window. Anyone?
I got a question.
From NVIDIA, I'd love to hear this offline. If you drop me a note about your application, that would be great. I'm sorry, I interrupted.
Hi, John. This is Joe. I got a question. Are you pushing forward on the graph blast effort, or do you consider that in the can?
Well, it's unfunded, so and the student has graduated. If we find a place where we think it can make more of an impact, and we believe certainly scaling it to multiple nodes would be useful, we'd like to be able to do that. You know, I think it pointed the way to a need for some more lower level primitives in terms of sparse matrix kind of operations, and some of those we developed, but I know that's something that your colleagues have worked very heavily on as well. And so to push the state of the art in that is something that I'm interested in. So if all you're doing is graph gloss in single GPU, I don't want to say it's in the can, but it's in pretty good shape. We don't have like this big list of things we'll necessarily like to do with it, but scalability would seem like a natural direction to go.
Thanks. Yep.
Hey, John.
Okay, great.
This is Brad.
Go ahead.
I was interested in your dynamic work. And is that going to be scaling out to multiple GPUs?
Whew. We would probably prefer to get some single GPU workloads that actually stressed it. I think one of the concerns we have is that whatever dynamic data structures you build, they're going to prioritize between a couple different things, right? Do you care more about, how often are you going to query it versus how often are you going to insert? And so, yes, we could do that given funding and resources and interest. Like, it's certainly a direction we could go. We have I believe you've seen our roadmap, but there's a lot of things we could do. We would like to know that that is something that's going to have an impact if we do it. In general, the dynamic data structure work that we've done, we have not taken to multiple GPUs simply because we haven't seen these use cases where, hey, there's this really interesting problem to solve and it's really going to fill a need. So obviously that's something I'm happy to hear more about.
Thanks.
All right, I think that's all the time we have for the questions. Again, thank you, Dr. Owens, for presenting, and we'd love to have you come back in the future for your new research work. Bye. And I think next we have Joe coming up to talk about CuGraph. Joe, you ready to share? Perfect. I can see your screen now. There we are.
Can you hear me?
Yes, we can hear you very
well.
well.
There we go. Okay, let me actually turn on my video also, so you can see me and hear me at the same time. All right, so I'll talk briefly about Rapids and CuGraph and how we can bring this together with the graph neural network, topic that we're all here to hear about. So here's what we're going to talk about briefly. Why do we care about graph analytics in the first place, right? John just talked a lot about it. I'm going to talk about it. What are some real down-to-earth use cases for this? What's Rapids? How does CuGraph fit into Rapids? I'll talk about half the time is going to be spent there. 7 minutes is going to be spent on the graph algorithms that we have and performance we're getting, including some Gunrock numbers, because we do use Gunrock inside of CuGraph. And then, how do we connect this into the graph neural network emerging ecosystem? And what benefit can we get from graph analytics in graph neural networks? Okay, off we go. So I'm going to use cybersecurity as my motivating example. A lot of people have heard about the recent SolarWinds hack. Cybersecurity is not a concern that's going to go away. If anything, it's going to get more important over time. And one way to imagine this is building a property graph with temporal information, either modeling network flows or user connectivity. And then you can compute certain graph analytics over time, PageRank, Jacquard similarity, use Louvain grouping to get communities and discover who talks to who most often, and then centrality measures to help you find who's the most influential in these groups. And then as you go through time, you can train recognizers, classifiers, to recognize anomalies relative to the baseline. And so there's a lot of vagueness in there, right? What is a baseline? What's anomaly? Well, that's what neural networks are really good at. So I'll talk about, what is our graph library and what is our vision for the CuGraph library? The vision here is to make graph analytics ubiquitous to the point that users just think of what problem they're trying to solve and not, how to use the tool and the toolkit that's got 15 different spanners and a Swiss Army knife and a couple screwdrivers in it, right? They would just like to focus on their problem of analysis and tying it to their real world problem. So towards that end, CuGraph is not just a graph, Swiss Army knife, right? CuGraph is one part of a bigger data science framework called Rapids. And Rapids is NVIDIA's Python-centric version of the pandas and scikit-learn packages. CuGraph comes in and tries to do an accelerated version of Network X. So when you put all these kind of common Python packages together, you can do a lot of things. And because the Python code doesn't change, what we've done is slipped in accelerated libraries that take advantage of GPUs under the same Python code. So anybody who's familiar with experimentation in Python or has their own custom Python packages can immediately take advantage of this for data preparation, feature engineering, model construction, model training, graph analytics, and along the way, maybe graph neural networks. That's where we're trying to go. And Gunrock, we use Gunrock for a lot of things. It has a lot of great features that John just talked about. So I'm going to move right ahead. The programming model is one of the most important aspects. John did a great job talking about that. And here's the block diagram of where CuGraph fits into this larger ecosystem. So we really have the image in our head of a user is a data scientist or someone trying to do some analytic task, and they have a loop that they have to go through to develop a useful system, some kind of a production quality system where they have to prepare data, train a model or run a model, visualize the results. If they're not happy with that, they have to go back to the beginning again, tweak the model, add different data, maybe add some different features. And we want to speed up this whole loop and make the whole loop end-to-end as fast as possible, because that's where you spend your time as a data scientist, is going around and around this loop. And because a lot of data scientists prefer the Python programming language to the user, all of our GPU code presents itself as Python. A user of Rapids doesn't need to write any CUDA code at all. They can just write Python code. We can have compilers. We have a package called Numba. It's not on this chart, but Numba is a compiler that can take Python code with some pragmas and compile it into a CUDA kernel. We can dynamically link that for user-defined functions that come from the Python world, but run as fast as CUDA functions. And we have the deep learning frameworks. We have our cuDF is our pandas data frame. Cormel is our scikit-learn like package, and CuGraph is like NetworkX. All of these together, they can connect with Dask to go multi-node, multi-GPU for scalability. And we all share a common binary format in Apache Arrow. So we can do zero copy transfers between GPUs or between GPUs and CPUs without reformatting arrays of data. So here's an example, right? So we've got lots of algorithms. The whole point of this is reducing cost and increasing performance for the data scientist. And we're doing that by improving integration with IO, data preparation, and machine learning, as well as graph analytics at the same time in one integrated package. So we talked about PageRank. This is one of the classic algorithms. I'm going to rip right through a bunch of these because these are very common things. Traversals are super important building blocks. Clustering algorithms, both spectral, hierarchical, local refinements. If you're doing a multi-scale method, something like Metis, or a multi-scale spectral method, you have this local refinement job you do in between scales. Then we have hierarchical clustering. So we have hierarchical Louvain, where we can repeat the clustering iteratively and recursively. And that gives you a more fine-grained idea of the community relationships. We have a really important feature that doesn't get enough attention, I think, is renumbering, and especially multi-column renumbering. When I'm reading in data from the real world, it's not automatically an integer between 0 and n-1, right? That's not how the world is. It's a bunch of strings. It's a bunch of IP addresses or port numbers or maybe bank account numbers, stuff that I can't use. I can't share it with anybody, and I don't want to use it internally in a matrix representation. So I need to renumber it back into that nice 0 to n-1. And we have a function in CuGraph that allows data to be renumbered very quickly and automatically, including multiple columns. So I can have an identifier, which is both an IP number and a port, or an IP number and a port and say a user. And that makes up one identifier in the graph. A lot of other systems have a hard time dealing with that without doing some manual coding. And we've allowed that to be kind of upfront, one of the things we handle for you. And this is the performance, right? So we can renumber 5 columns. This is, one identifier, 2 identifier, number of columns in the identifier. So up to 5 columns combined into one ID. If one of the columns happens to be a string, it slows down a lot, but that's one of the most useful aspects also. But the point being here, we're renumbering 10 million edges here in a handful of seconds, right? So 1 million a second, you can renumber and get a nice compact integer renumbering. Okay, that's the quick stuff. How am I doing on time? I think we've got a little more time. So I'll talk about performance. So our goal is to take the ease of use of Network X and let you run what you're already doing in Network X 1,000 times faster, right? And that's what this chart is showing. If you're using Louvain in Network X, it's really slow if you're doing anything bigger than a couple hundred vertices usually. When you get to real world or reasonably sized millions and tens of millions of vertices and edges, Network X is unusable. And that's where CuGraph can really help. We can give you the same functionality 1,000 times faster. You can get your job done and not wait around. Talked about PageRank. PageRank has been done forever. We have multi-GPU PageRank. We have really good numbers on this. Nothing really shocking here. BFS using Gunrock. Here's Gunrock's numbers using multi-GPU. These are kind of out of date now, but the whole point here is showing it scales with multi-GPU, it runs at large scale, and it's just out of the box, gives you good speedups. Okay, this is the interesting part. If you haven't heard anything yet, this is where things get interesting. So what do we do in a graph neural network, right? We have to pick some set of features. Then we want to train the neural network to recognize the labeled data given that set of features, in the future, right? So choosing the set of features is really important. And one of the things we've learned is graph analytics provide really good features. So I've got just an internship just finished and just presented today at NVIDIA on training a graph neural network and a gated recurrent unit hybrid to learn temporal data as a graph, the net flow graph changes over time to identify botnets that are hiding in a given network. And this is the set of features we used. We took the net flow data. It has pre-calculated durations, IP addresses, protocols. We pre-processed all of that using CuDF to find min, mean, packets, summations, aggregations. We added on PageRank between the centrality, cat centrality, and degree calculated from CuGraph. And then we trained the graph neural network using those features. And then we tried it without those features. And this is the interesting thing. We see with just the net flow features on the left, it's really hard to identify there's 3 bots in here. When you add in the graph analytics features, the 3 bots separate out and kind of jump out at you and say, ha, there's 3 of them, which is not obvious from just the net flow features. Now, this is not, this is UMAP, right? UMAP is projecting these 15 features down into a 2-dimensional representation. So UMAP is able to make this nice separation. And my claim here is that graph neural networks and deep learning can also discover this along the way. And the results show that, yes, we are getting much better accuracy in the graph neural networks when we add in these graph analytic features. And that's really, one of the immediate things we can offer here with the graph neural network users is giving them accelerated data processing and accelerated data analytics as really good features to add into your models. We talked about Network X. We're not going to stop just with Network X, but it's a really good place to start. Network X is a complete standalone package, right? It has a nice workflow. You load data, you create a graph, you do some things to the graph, you run some analytics. It's dynamic. All Network X graphs are naturally dynamic, which people may take advantage of or may not even know they're taking advantage of it because it's just so natural in Network X. CuGraph is designed to be a non-persistent form. So we throw away graphs a lot. We'll build them and throw them away, build them and throw them away. We don't modify them. We don't add and subtract nodes very much because of the problems that John mentioned, right? The CSR data structure that's underneath here is not very dynamic. So we're forced into this repeatedly building and throwing away. But the point is, if the user doesn't care about the back-end data structure, they can use their favorite API. They can get really good performance and ease of use and ease of programmability and ease of developing and solving your problem with the Network X API running on CuGraph. And then the other angle we're taking is the data frame centric approach of data preparation, data cleanup, feature engineering. That's kind of orthogonal to Network X, but also necessary and complementary because Network X is just a graph thing. It doesn't know about ETL processes and data cleanliness and pandas operations. So we bring that in as an enhancement. So here's an example of how CuGraph compares to Network X. In Network X, you take an edge list, say COO list of edges, source and destination, in a data frame, say, and you can build a graph from that data frame. And then in CuGraph, you can build a graph object, and you can load an edge list and run the same exact algorithm with the same code. The interesting thing here is this can be interchanged. So I can actually read data from a CPU, read it from a GPU. I can construct my data on the CPU and copy it over with Apache Arrow with no transformations required, and run it on the GPU in place, essentially. And matching super close is really important because we don't want users to think about how to rewrite their code. We want them to solve their problem and then use CuGraph to solve their problem faster. So we're trying to make it even easier, right? Even shorter amount of code you have to write to use CuGraph effectively to do PageRank. Why do we have to build a graph explicitly? I say, here's a source and destination list. It implies a graph. Please build that graph for me and then run PageRank on it in one line. That would be great, right? So we're building up a set of even shorter and more concise APIs. The roadmap going forward, we've got a lot of plans for going to bigger scale, multi-node, multi-GPU. Performance is always one of the top concerns. And we have a lot of automation, like I mentioned, shorter APIs. We have a lot of GNN work. We have all right, thank you. Let me go back one. So GNN acceleration, we have some features in EgoNet I'll talk about in the next slide. EgoNet extraction is extracting a set of subgraphs for each vertex. And this is a key step in training or inferencing using graph neural networks. So we're actually adding an EgoNet extraction feature specifically to accelerate graph neural networks. Better property graph support. Property graphs, again, that's kind of ubiquitous data format for graphs, right? Everybody loves property graphs because they very closely match the reality of messy data, right? Entities have properties, relationships have properties, and immediately you're into the property graph world. So we're building up a richer set of features for dealing with property graphs and dealing with all these associated data that comes along with real world graphs that aren't academic, a list of edges anymore. They're much more rich data along with the edges. It's not just the graph connectivity, it's a whole relational table along with it. And of course, always more algorithms. let's talk about the EgoNet. So here's the API we're proposing for a batched EgoNet, where a batch means I want to do a whole set of vertices in one go and get the results back in one return value instead of having to call it again and again and again for every vertex. In NetworkX, this is a one vertex at a time. With a GPU, we don't need to do that. Someone's taking over here. Let me see. So I think we're being call it Zoom attacked, right? We're getting a lot of So at this point, I guess I'm open for questions. Are there any questions from the audience?
Hi, Joe. So this is Mingjie.
Hi.
Yeah. So I have questions about because you said that one of the major goal of CuGraph is to have basically network like one-click user experience from NetworkX to CuGraph, right? And this is something actually DGL also tries to do, like in the very beginning of the very early age, and we eventually found that some of the NetworkX interface is not designed for those like batched processing, right. Which turns out to be difficult. And how would you like handle that?
Yeah, that's exactly what we're hitting also. We're having to expand the NetworkX interface to add in these batch operations for efficiency. NetworkX never imagined operating at the scales that we need for graph neural networks or for large scale graph analytics. So we're having to extend it and add in new APIs that are similar, but go beyond. Yeah.
Yeah, I see. Yeah, that's similar to what we are doing. Yeah. Okay, cool. Thanks.
So Joe, if you don't mind, one of the things that we also did was allow for NetworkX objects, graphs to be directly passed into CuGraph functions. So you can build all your graph in NetworkX, and then instead of saying NetworkX PageRank, just say CuGraph PageRank and give us that object, and we operate on it.
Yeah, do the conversions behind the scenes that need to happen. Yeah. So all your graph construction code, all your data loading code doesn't have to change. You just hand off to CuGraph for some analytics. Thanks, Brad. So Brad is the manager, lead of the CuGraph team. So he's much more involved in this on a daily basis. I'm all over the place with graph neural networks and customer visits and all kinds of stuff, but Brad is the guy getting it done day to day.
No, I'm the guy who's like with the whip getting everyone else to get it done day to day.
Hey Joe, this is Leo from Graph History. I'm curious with respect to priorities for today. If you have anything to say about single GPU versus multi-GPU, more algorithms or more depths in the algorithms, because it's hard to do all the things at the same time. So I'm just kind of curious how you guys are thinking about it.
Yeah, we're trying to be driven by customer needs, and a lot of customer needs require multi-GPU as a table stakes, right? The problems are too big to fit in a single GPU. We'd love to work with customers with data set sizes that fit in a single GPU already, and we do work with quite a few of those already, but more and more of them are demanding more scalability, and that means we're being forced into multi-node, multi-GPU as a top priority. And porting all the existing algorithms we already have single GPU to work multi-node, multi-GPU, which is a long process, right? We can't do that overnight. But Brad, do you have any comments? What's your opinion?
So we're trying to move to a new graph primitive model that will support single and multi-GPU. So whenever we write a new algorithm, just by basing it on those primitives, it automatically scales. But we're running into, trying to figure out how to optimize those so that they run fast in all situations.
And when you say multi-GPU, it sounds like you also mean out of core, like bigger than memory.
Currently, well, we use unified memory for that case. And we are thinking of how to do true out of core, but that's another thing on the roadmap that just.
So there's a whole data preparation phase or feature engineering phase of managing big data sets, petabytes of data, where that's not how big the graph usually is, but that's how big the data you start with is. And you extract a graph from that, or many graphs from that. And that's where we have a lot of work on accelerating that extraction process and graph construction process, but not necessarily storing the petabytes of data on GPUs. Those petabytes of data probably stay on the host side or on disk even. Yeah.
Hi, Joe. So I have another question. Yeah. So one of the problem we met in DGL is like some of the graph algorithm. Actually, most of graph algorithm is data dependent. So basically that means the algorithm, in order to achieve the optimal performance, need to actually, for example, reorder the graph and change the graph layout, right?
Yep.
And but that is also costly. So is there any solution to that? Like, I'm always wondering.
Yeah, I mean, load balancing, right? John did a great job of discussing the load balancing problem, right? That's really key. I mean, load balancing is in your face immediately with graphs because it kills you if you don't have some way of dealing with it. And that's really adapting to the data. That's one way of saying you adapt your algorithm to the data by load balancing your algorithm.
You mean you don't need to change the data layout? So it's more like the algorithm should be like smartly looking for the opportunity of load balancing, and we can avoid changing data layout into such case.
That's what we're working from. And John, is that how it works with you?
That's also the Gunrock philosophy.
Yeah.
I mean, like I think one sort of big picture thing is, do you get to pre-process your graphs or not? Right. And so you could pre-process an input graph if you knew you were going to use it a zillion times, and there's use cases for that. And maybe you do some sorting or other data layouts that make sense. That is not Gunrock's philosophy. Gunrock feels that it's going to be more like a rapids thing where you have this big string of things, and the first time Gunrock sees this graph that's when you start computing. And so we feel that we want to do well on data sets that come in that we haven't got to pre-process. And that's been our focus all along.
Yeah.
I see.
Yeah.
Yeah, so actually in GNN we have both situation. Like one is what you said, the graph is static and we can pre-process it in order to have a better layout. The other is the sampling algorithm where we extract these ego networks from a larger graph, and ego networks are generated on the fly. So we cannot even have the chance, like adding an overhead to the data layout conversion is not acceptable. Yeah, so both cases happens here.
Yeah, and I think it's going to get more complex, as we develop more rich GNN, our use cases, right, and property graphs, and it gets harder. So we have to think carefully about how to take advantage of what we can at runtime, and still think ahead for not getting hit with the worst case with some data that just happens to be pathological for a given algorithm. Yeah.
I see. Thanks.
Great. Thank you, Joe. Any other questions before we go to Professor Shi?
Okay. Thanks, guys.
Great. Thank you, Joe. And let's see. So Professor Shi, we're ready for you. So you can go ahead and share your screen. Should work now.
Yeah.
Welcome.
I'm here. Yeah.
Yeah, you should be able to share your screen now.
Okay.
Yeah, we can hear you very well. Perfect. We got it. Thank you. We'll let you start.
Okay. Can you hear me?
We can't hear you very well. Thank you. Yeah.
Okay. Oh, hi. Good afternoon, everyone. I'm Chuan from Beijing University of Posts and Telecommunications. Thank for Minjie's invitation. It's my great honor to give a talk. Our recent work in graph neural network. The title is sorry. Okay. Oh, okay. The title is Revisit the Learning Mechanism of Graph Neural Network. Okay. We know that the graph or networks are general language for describing and modeling complex systems. For example, in social networks, a person is a node, and the interaction between the two persons is a link. So we can construct the social networks. Other examples can be seen in the economics network, biomedical networks, information networks, and so on. An important task in a network is the learn the structure property of a node. Traditionally, we can represent the node structure with adjacent matrix. However, the adjacent matrix is usually very huge. So it motivates us to embedding the node of a network into a low-dimensional vector space, which preserve the graph structure and properties. The node embedding can be easily used in the downstream applications, such as node classification and link prediction. And network embedding is easy to parallel, and we can apply the classical machine learning method for the node embeddings. So many network representation model has been proposed. They can roughly classified into two types. The first type is shallow model. They also can be classified in two types. The first type is a factorization-based approach, which is widely used in collaborative filtering, such as Laplacian eigenmaps. Another type is a random walk approach, lightened by the word-to-vector. Many random walk approaches employ the deep walk to get a node sequence. The two adjacent node in the sequence has a close embeddings. The representative methods are deep walk and node-to-vector. Another type is deep model, which apply the deep neural network for graphs. It also includes two types. The autoencoder approach employ the autoencoder to reconstruct the graph, such as the DNGR and SDNE. Another type is GNN, whose basic idea is that a node has a close embedding with its neighbors, so it averages neighbor information with a neural network, such as the GCN, GraphSage, and GAT. The graph neural network has been a hot topic in AI. It not only has excellent ability to learn the structure property from graph, but also provide a powerful tool to exploit the hidden patterns in text and images. Let's give more detail on the learning process of GNN. Given a graph A and load feature X, it first initializes the embedding with the node feature. Then it iteratively aggregates the labels embedding. Finally, it makes a prediction with a softmax function. From above analysis, we can find that the GNN has some advantages. Well, there are some corresponding deficiency. Firstly, the GNN provide a good mechanism to fuse features and typology. However, is the fusion mechanism optimal? Secondly, many aggregating strategies have been proposed. However, is there a uniform framework for those aggregating strategies? Thirdly, many research has pointed out that the GNN is a low-pass filter for graph singular. However, is the low-pass filter enough for different kind of graph? In this talk, we will revisit the learning mechanism and present our work in three aspects: fusing mechanism and aggregating mechanism and frequency mechanism. Firstly, we'll start the fusing mechanism. We know that the GNN and its variants follow the message passing mechanism. That is, the node feature propagate and aggregate along the network topology with an end-to-end semi-supervised learner manner, and the node label guide the learning process. The greatest success of GNN line the good mechanism of GNN to fuse the features and topology. However, is this fusion mechanism is optimal for what kind of graph? Let's first say experiment investigation. We do experiment to validate the fusing capability of GCN with two extreme graph data. In the first case, we generate the graph with random topology and created load features, where the load features are generated from the three Gaussian distribution. In this case, in this case, we run the MLP and GCN for the node classification. We can find that the MLP achieved the 100% accuracy, while the GCN only has 75% accuracy. It is reasonable because the MLP only handled the node features, while the random topology hurt the performance of GCN. In another case, we generated graph with created topology and random node features, where the node are generated from three community. We also run the deep work and GCN on this data set, we can find that the GCN achieved 100% accuracy, while the GCN only had 87% accuracy. The result is also reasonable because the deep work only handled the structure, while the random node feature hurt the performance of GCN. From the experiment, we can find that the fusion mechanism of GCN is distant from optimal. So it motivates us to adaptively extract most correlated information of the structure and features according to the task. Following this idea, we designed adaptive multi-channel graph convolutional networks named AMGCN. The basic idea is that the labels of tasks guide the automatic fusion of features and topology. AMGCN include two key components. The first one is to extract the specific and common informations the first one is to model the relation and the feature and topology by extracting specific and common informations. The second one is to automatically learn the fusion weight with attention mechanism guided by task for adaptive fusion. Let's get more details. Firstly, in order to capture the structure from features, we construct a feature graph with the KNN distance of the features. Then we extract the specific information with a specific convolution model. Furthermore, we extract the common information with shell pyramid convolutional modules. After that, we automatically learn the important weight of three types of embeddings and then adaptively fuse them. In addition, we also designed two normalization terms to constrain the learning process. The disparity constraint make the disparity constraint make the specific embedding and common embedding independent with HSIC query. And the consistency constraint make the consistency constraint make the embedding of the common embedding from the topology graph and the feature graph close with the L2 distance. Finally, we get the optimization, which includes the three components. The first one is the prediction loss and two constraint term. the experiment on load classification illustrated the best performance of the proposed AMGCN. And we can also find that the AMGCN can automatically learn the weight of typology and features according to the different tasks. Let's say the example in UAI dataset, we can find that the weight of the feature is very high because the feature is very rich in this dataset. And another example, the Quarrel 4, the weight of typology is very high because the feature in this graph is very weak. So our algorithm can automatically detect which part is more important. Then we'll always study the propagation mechanism of GCN. We know that the propagation mechanism is the most fundamental part of GCN. Different GCN has a different propagation mechanism, and so many propagation mechanisms have been proposed. So, to essential question need to answer: is there a unified framework to govern the propagation mechanism of different GNN? And if so, can it bring new insight for new GNN designing? Let's first revisit the propagation process. Given the node feature and graph typology and the iteration number k, the propagation union aggregated labels embedding along the graph topology and do transform operation. Many propagation has been proposed. The union for obtain two goals. Employ the network topology as a low-pass filter to smooth the features, and use the node features to restrain the representations. This propagation can be unified in this framework. It includes two parts: the fitting term to restrain the representation with the node features, and the graph regularization term to smooth the features with the network topology. With this unified framework, we can interpret the existing GNN, and we also can design the new GNN through the denoting the graph conventional kernel or the changeable coefficient. First, we interpret existing GNN. For example, the GCN, we can rewrite the GCN and SCG in this equation, the only with the graph regularization term. And we can also do the same thing for other GNN. Furthermore, we designed new GNN by by denoting the graph convolutional kernel, F1 and F2. For example, we designed F1 and F2 in this equation. In fact, it is a low pass filter. Then we can get the closed solution and the iterative approximation. Similarly, we can also design the F1 and F2 in this equation. In fact, it is a high pass filter. We can also get the closed solution and iterative approximation. Let's say the experiment. We can find that the proposed GCN, HF, and LF get the best performance. And the proposed model can elevate the over-smoothing since their performance are very stable with the increase of the propagation dips. Finally, I will introduce the work on the frequency mechanism. We know that the node feature and the labels can be said singular on the graph, and the GNN can be considered as the frequency filter on graph. Many research has pointed out that most existing GNN usually employ the low frequency singular, such as the GCN, GAT, and SCG. So it motivates us to answer the following question: is the low frequency information what we needed? In order to answer this question, we do experiment to validate the role of low frequency singular and high frequency singular. Specifically, we tested their performance on node classification with a series of artificial networks. The main idea is to greatly increase the dissortativity of the graph, and then we observe how the performance changes. From this graph, we can see that with the increase of the dissortativity of the graph, the performance of low frequency singular degrade, while the performance of high frequency singular rise. This experiment shows that the different frequency has a different role for GNN. Specifically, the low frequency singular perform better on assortative graph, and the high frequency singular perform better on dissortative graphs. So, two essential questions need to answer for design new GNN: how to use the singulars of different frequency in GNN, and how to make the GNN suitable for different type of networks. The basic idea is that different from traditional GNN aggregating label only with the low pass filter, our fun GCN aggregator labels with the low pass filter and high pass filter. The right figure shows the framework of our fun GCN. We designed the low pass filter and high pass filter to distinguish the low frequency singular and high frequency singular, and then combine these singular with different weight. However, the singular combination has two shortcomings. It has a high computational cost because of the metric production, and it also lacks the inductive ability. So we rewritten the equation and infer the spatial version. In this equation, we can see that the fun GCN also aggregated the labels with attention value. However, different from traditional attention value being positive, our attentional value can be negative and positive, which make fun GCN flexible, aggregate the assortive label and disassortive labels. The fun GCN has good properties. The low passing filtering make the representation become similar, while the high passing filtering make the representation become more discriminative. The experiment showed that the fun GCN achieved the best performance on assortive graph as well as the disassortive graphs. And the fun GCN can also elevate the over-smoothing problem. Finally, we gave a brief conclusion. Although GCN have achieved great success, they still have many shortcomings. Investigating the learning mechanism of GCN will benefit the design of GCN, and many work are also being explored, such as the theoretical analysis, such as the learning mechanism and expression power, and some hot topic also can be explored, such as the self-supervised attack and pre-train. And a reliable GCN is also important questions, and we can also do more applications on security, graphical and software with GNN. More materials can be found in our survey paper and in my web page. Finally, thanks for your attention. Yeah.
Thank you, Dr. Shi, for the great presentation, and also all of our speakers today, including Dr. Owens and Joe Eaton, Dr. Joe Eaton. And so what I'd like to do is to open the floor for questions.
Hi, I have a question for Dr. Shi.
Yeah.
So on your slides page 14, I'm wondering what's the purpose to use the two different constraints?
Which page?
14.
14. Okay.
Yeah, so in the objective function, there are two different constraints, disparity and the consistency. I'm wondering what's the a purpose to use like this kind of constraint?
Okay. The disparity constraint to make the embedding, the specific embedding and comma embedding as different as possible. And the consistent constraint, consistency constraint make the comma embedding of the typograph and the feature graph as close as possible. Make these two same and these two different.
So is the intent here like a saddle point problem, a min-max problem you're solving? Want to maximize disparity and minimize inconsistency?
Sorry?
I'm saying, is this similar to a min-max objective? So you're trying to maximize the disparity value and minimize the inconsistency.
Let me check. Minimize. Yeah. Minimize this objective. Yeah. For example, minimize LC to make the ST and the SF to be close. Yeah.
Okay. Thank you. And for page 25, there's some picture like a heat map. I don't know what it is.
Yeah.
25.
25.
There's a result. Yeah.
Yeah. Oh.
So there are four pictures in the bottom of the slides, and it's like model analysis. I don't know what is that.
Okay. In fact, it's a parameter analysis. The alpha and u is two parameter. Let me say the alpha and u. Yeah, the u and alpha. These two parameter. Yeah, it control the different part component. Yeah. So there are two parameters in the function. We say the how the performance change with these two parameters. So we draw this this picture. Yeah. It shows the performance. The more read, the read is more accuracy. We can find that when we change the alpha and u, we can see the performance. Yeah, we can say that on the Quora data set, the performance is not sensitive to the parameter mu. However, it is sensitive to the parameter alpha. Yeah.
Yeah, thank you so much.
Any other questions? Okay, well, thank you, Dr. Shi.
Okay, thank you for your attention.
Yeah. So and I want to just kind of conclude the conclude the session here, and we then can open up the floor for everyone to chat a little bit. So first of all, I want to thank everybody for your patience, and I know that we got a little bit of Zoom bombing today, but we survived it and we did very well. So I want to thank everyone for your patience and also your support for this user group. We'll continue to run this every month, and we're thinking about also running this on the very same day at 8 a.m. Pacific next month in March for a European session, so that folks in Europe can actually take advantage of the user group. We'll make an announcement there. But I think the most important thing is that we should, everyone should have the link to the to join the Slack channel. So we'll be making most of our announcements there. And I just shared that link there. So make sure that you are part of this, part of the user group inside the Slack channel. Slack channel is going to be safer. And in addition, that we'll be making, we'll have other type of discussions. And if you have any questions about DGL, about CuGraph, about any of the sessions that we went through today, we've already posted all of our presentations there as well. So we hope that that will be like one place where we have a way of reaching out to everyone, so we don't have to keep doing emails among other things. So. So now I would like to open up the floor for folks who want to introduce themselves. Perhaps you can talk about what type of work you do, or which company you work for. If you have any questions, what you would like to get out of this user group. So I'll open up the floor. Anyone would like to speak first? Don't be shy, or introduce themselves.
I'll volunteer to help kick it off. Leo, founder over at Graphistry. We do GPU accelerated visual graph analytics, so end-to-end stuff. And so we have a lot of fun taking the results of machine learning models and making regular users able to understand what's going on, and help a little bit with data scientists themselves trying to inspect their models. So if you use Jupyter Notebooks, you should probably check us out.
Thank you, Leo. Really appreciate it. Yeah. And I also like to introduce the team that has also been helping out with the organization. So Joe Eaton has been helping quite a bit, and also Ming Jie. He is the tech lead on DGL, and he just released, we just released 0.6. So definitely feel free to be part of the Slack channel. If you have any questions about our 0.6 release, we'll be very happy to answer your questions there. And also Xiaoying, and Xiaoying works with Joe over at NVIDIA. And let's see, Grace. Grace and I have been the partner in crime in helping organize this. And I also see Meryl Inov. He's a solutions architect at NVIDIA. And lots of people also from the DGL team. Yeah, so definitely feel free to talk to folks, and hope to meet others at the Slack channel. Anyone else want to maybe introduce themselves, or if you have a topic that you would like to suggest you would like to present, we'll be very happy to try to find the right speakers for the next session.
I'd like to nominate Leo. I'd like to hear what you're up to lately, Leo.
Okay.
Maybe not next one, but maybe the one after. Then we could do
All right.
visual deep learning.
we'll sign you up for April then. Yeah.
I second that. I'm a big fan of Leo.
Fantastic. All right. Thank you, Brad. Anyone else have any questions? And for those of you who are looking for internship opportunities, we do have a few opportunities. Amazon hires a lot of interns, so just feel free to reach out directly to me. And my contact information is wye@amazon.com. So if you're interested in any kind of internship, I will be very happy to provide these opportunities. And I know there are a few professors here, so if your students are interested in such opportunities, we'll be very happy to talk to them. And also, I'm sure there's internship opportunities in NVIDIA. Joey, want to talk about that?
Exactly.
It's the season. It's the season.
Yes, exactly. We always have a large, crop of interns every spring and fall as we, bring people over. We do a variety of different lengths of internships. Anything from 4 weeks up to, I think our record is 1 year for an internship. But we have openings in almost every group for interns. Anything you're interested in working on in the Rapids whole world is available for internships.
That's great. Yeah. Anything else?
I guess.
Go ahead. Yeah. Go ahead.
I guess, Brad, do you want to say anything here?
So as Joe mentioned, I lead the CuGraph effort. So I have a team of engineers under me doing all the development work. I'm always eager to see, what people are doing, how they are using things, what they need to see in tools. And, always interested in interns and full-time people who love graphs.
Fantastic. Anything else anyone would like to share or talk about? We have a few minutes left.
Thanks for organizing, Wenming. This was a great session. Lots of good content.
Yeah, thank you. Thank you, Joe. And thank you for being so patient on the minor glitch we had today. So now I understand how to lock the room. So those are all skills that we learn for virtualizing everything. All right, I think
Wenming, the last thing that I want to add is for everyone. Yeah. So what I will do is I will add a link to the survey in the Slack channel. So if everyone can please take a moment to kind of fill it in, let us know what kind of topics they're interested in for the future to make sure that we have those sessions in the upcoming events.
Absolutely. Yeah, we'd love to hear any kind of applications of graph neural networks or ideas that are out there for more interesting things happening with graph neural networks. It's a really, really exciting space these days.
Okay, great. So I guess we have a couple minutes left, and if I don't see any other folks that want to share anything, we'll call it a day. And once again, I want to thank our speakers and also everyone for being a great audience here. And we'll see you next time. And thank you, John.
Thanks, everyone.
But thank you. Thank you, Dr. Xu. Yeah. And also thank you, Joe. Yeah. Hopefully we'll have all of us back at some point very soon. Yeah. So this is, like I said, this is a community for everyone. It's everyone's user group. It's everyone's user group. So thank you very much again. Yeah. We'll see you next time.
Thank you. See you.
Bye.